Now we come to a different NMR spectrum. This particular spectrum is a proton NMR spectrum of methyl fluoride. The methyl hydrogens of the methyl fluoride are, as in the case of methyl iodide, all equivalent. We speak of these three hydrogens comprising a single set of three equivalent hydrogens. There is one signal peak produced. The peak occurs at about 4.3 delta value. For reference, we show the signal for methyl iodide as seen in the previous NMR spectrum. Of course, we also see the inevitable TMS peak set at 0 delta. The NMR signal for methyl fluoride occurs at a larger delta value than that for methyl iodide, and here's why. Fluorine is a more electronegative atom than iodine, and thus pulls more strongly on the electron cloud enveloping the protons. And thus, the density of the electron cloud about the protons of methyl fluoride is less than the density of the electron cloud about the protons of methyl iodide. This causes the observed delta value for methyl fluoride to be higher. It causes the signal to shift to the left in the spectrum. The reduced electron cloud density creates a stronger net magnetic field about the signal nucleus. This results in a higher frequency of spin for the nucleus, and ultimately, when you do the math, creates a higher delta value. In general, any structural effect that lowers electron density of the electron cloud surrounding the spinning nuclei causes the peaks to shift to the left, becoming a higher value of delta. Peaks that are shifted to the left are said to be de-shielded, and those that are shifted to the right are said to be shielded. In general, groups that inductively withdraw electrons have a de-shielding effect on nearby signal nuclei in the NMR. Groups that inductively donate electrons have a shielding effect on nearby signal nuclei in the NMR. Now, there are other electronic magnetic effects on shielding, de-shielding that we'll discuss in a later video. Here is another NMR spectrum. This is a proton NMR spectrum of an ester. The ester is called methyl acetate. There are two methyl groups in the molecule. Each methyl group comprises an equivalent set of three protons. So each methyl group generates one signal. 1, 2. Thus we see two signals for the ester. And as always, of course, we see the peak at 0 delta for the added TMS standard. Which methyl is which? Well, it turns out that an oxygen atom has a stronger electron withdrawing effect than a carbonyl group. Consequently, the oxygen of the methoxyl has a greater de-shielding effect on the methoxyl methyl, a greater de-shielding effect than the methyl bonded to a carbonyl group. And as a result, the methoxyl methyl occurs at a larger delta value. It occurs at about 3.6. The methyl bonded carbonyl group occurs at approximately 2 ppm. Now, there's also this. both of these peaks are the same peak area, and that's significant because peak area is proportional to the number of protons that give rise to that peak signal. Each of these signals is associated with a methyl group, so therefore both of these should be the same area. Well, it's not so easy to measure precisely the area of a peak, and so the instrument has a way to do that. It's called peak integration. After obtaining the spectrum, you put the instrument into what's called a peak integration mode. And in one approach, what the instrument does, or the computer associated with the instrument, is to draw a stair-step line at each NMR signal. That's what we're seeing here. It turns out that the height of this stair-step line is proportional to the peak area. Now, since both peak areas are going to be the same, they're each due to a methyl group, the height of the stair-step lines, and as you can see, are approximately the same. So we can use peak integration to determine the relative areas of signal peaks, which will tell us the relative number of protons associated with each signal, with each peak signal. Here's another spectrum. This is a spectrum of 1,1-dichloroethane. This particular spectrum is done also at low resolution. Because it's done at low resolution, one of the things that we note is that the peaks for it are broader than what we've seen before. Well, we can still determine which peak goes with which protons in a molecule. This molecule has two equivalent sets of hydrogen. It has the methine hydrogen, the single hydrogen, that comprises one set, and it has the three methyl hydrogens, these three equivalent methyl hydrogens, that comprises the second set. Now, this single hydrogen, notice that it's on a carbon attached to two chlorines. The methyl hydrogens are further away from those chlorines. The chlorines are electron withdrawing atoms. Since the single methine hydrogen is closer to the electron withdrawing chlorines, that causes the single hydrogen to be more deshielded than the methyl hydrogens. With a greater deshielding, the signal for that hydrogen is shifted to the left. So this little peak right here is the methine hydrogen. The other peak is the methyl signal. Alright, let's rerun the NMR spectrum of this compound, 1,1-dichloroethane, but this time let's do it at high resolution. Let's take a look at the high resolution spectrum. Aha! Looks quite different. What's happened is that these two broader peak signals have become split into multiplet signals. The methine hydrogen signal becomes split into four narrow peaks. That's called a quartet. And the methyl signal becomes split into two narrow peaks. It's called a doublet. What we're seeing here is a general phenomenon called spin-spin splitting or spin-spin coupling. In a nutshell, each set of signal protons is split into a multiplet of peaks, and this splitting is caused by the magnetic influence of the protons that are neighbors to the signal protons in the molecule. Let me explain. The methyl hydrogens in the molecule as signal protons are neighbored by the methine hydrogen. So this signal is due to the methyl group. The methyl protons in the molecule are neighbored by the single methine hydrogen. The single hydrogen is going to exert a magnetic effect on the methyl signal, and as we'll explain, that causes the methyl signal to be split, in this case into two peaks. Now the methine hydrogen as a signal proton, as it plays out, it is going to be influenced by the neighboring CH3 hydrogens. The neighboring CH3 hydrogens are going to magnetically influence the methine hydrogen, causing it to be split into a multiplet of 4 peaks. Now let me try to explain from the ground up what's going on here with respect to spin-spin splitting, also called spin-spin coupling. The next slide we'll use this diagram to try to understand what's going on. In this particular case, we have one carbon bearing a hydrogen attached to an adjacent carbon bearing a second hydrogen. Now, one of these hydrogens we'll regard as the signal proton. The other hydrogen here we refer to as a neighboring proton. The proton on the carbon adjacent to the carbon bearing the signal proton is in fact called a neighboring proton. Now the neighboring proton, this is true with any spinning nucleus with an I of 1/2, has two directions of spin. To make it simple, we'll refer to it as being spin up or spin down. Now let's say we have 100 molecules. Approximately half of these molecules, the neighboring hydrogen will be, let's say, spin down. The other half of molecules, this neighboring hydrogen, will be spin up. Well, each neighboring proton, depending on its orientation, is going to create a local magnetic field that our signal proton is going to feel. But because the neighboring proton is in two possible orientations, the signal proton is going to experience two different local magnetic fields. Half of our 100 molecules, about 50, the signal proton will experience a local field for neighboring hydrogens that are spin up. The other half, around 50 molecules, will experience a local field for neighboring protons that are spin down. Consequently, our signal proton being under two different local magnetic fields, it's going to create two different signals, a doublet. Alright, let's look at another situation. In this diagram, we're going to assume that we have one signal proton as before. The carbon attached to it this time bears two hydrogens. These we'll regard as two equivalent hydrogens, two equivalent neighboring hydrogens. Now, each of these neighboring hydrogens, of course, can be either spin up or spin down. If you think about it, you realize that our single proton, compared to the previous case, is going to experience a greater number of local fields from these neighboring protons. What's the total number of local magnetic fields it'll experience? Well, we can look at it this way. The two neighboring protons can both be, they can both spin in the same direction, let's say spin up, or they can both be in the same direction, spin down. Or one can be spin up and the other spin down. If you count them, that corresponds to three different local fields created by the neighboring set of protons. 1, 2, 3. So our signal proton, feeling three different local fields from the neighboring protons, it's going to create three NMR signals, a so-called triplet. Now let's look at another situation. In this case we have one signal proton as before, but we have three equivalent neighboring hydrogens. Three equivalent neighboring hydrogens on the carbon adjacent to the carbon bearing the signal proton. Well, with three neighboring hydrogens, there are a larger number of local magnetic fields that our signal proton is going to feel. How many are there? Well, all three of our neighboring protons could spin in the same direction, let's say spin up, or they could spin in the same direction, spin down. Or one could be spin up and the other two spin down. Or one could be spin down with the other two spin up. If you count them all up, that's going to become four different local magnetic fields. 1, 2, 3, 4. So our single proton feels four different local fields, and it's going to create then four different signals, or a quartet.